It talks about the second order circuits. So let's start. So second order circuits are basically characterized by second order differential equations, and it consists of resistors and two equivalent sources of or two equivalent sources or two equivalent passive components which can store energy. They can be either a resistor, they can either be a capacitor or an inductor, or they can be two inductors, they can be two capacitors. So it can be anything. So any combination of these or something like this will have a differential equation of second order. So here in the first diagram, we see a series combination of RLC circuit. In the second diagram, we see a parallel combination of RLC circuit. Again, in both of these circuits, we have two storage elements, an inductor and a capacitor. Similarly, a capacitor and an inductor. And then we have a combination of two resistances and two inductors. Again, this is a second order different circuit or a second order differential equation that governs the circuit. We have two storage elements, 1 and 2, because these are two inductors. Similarly, here we have again two storage elements, one capacitor and a second capacitor connected with a resistor, and there is a current source that is supplying. So these all are the examples of second order circuits. So moving ahead, the first topic in this chapter is regarding finding the initial and final values. So before we go into or we start solving the initial and final value problems, the key thing we have to remember is that the capacitor doesn't allow instantaneous change in voltage, and the inductor doesn't allow instantaneous change in current. Remember the differential equations which we saw earlier. So for the capacitor, we have current through the capacitor is given as C times dV, C divided by dt. Similarly, the inductor voltage is given as inductance times current through the inductor, rate of change of current through the inductor. And we also know that any variable that comes with a differential sign or with a derivative sign, that doesn't changes instantaneously, and it's a mathematical property. So we can say from these differential equations that the capacitor voltage can't change instantaneously, and the capacitor current and inductor current can't change instantaneously. For a resistor, remember, resistor is again a passive element, so the voltage across the resistor or the current through the resistor both can change instantaneously, whereas across an inductor and a capacitor, remember this is the symbol for a capacitor, this is a symbol for the inductor. For an inductor, current through the inductor cannot change instantaneously, and voltage across a capacitor cannot change instantaneously. Okay, so keeping these points in mind, let's try to solve a couple of questions to clarify these concepts. So we have example 8.1 of our textbook. In this example, it says that the switch in figure 8.2 has been closed for a long time. So it's basically talking about the switch. It's been in closed situation for a long time, and it is open at t equals to 0. At t equals to 0, the switch is thrown like this. We have to find these values: I at 0 positive, voltage at 0 positive, rate of change of current at time t equals to 0 positive, rate of change of voltage at time t equals to 0 positive. And we have to find out I at infinity and V at infinity. So first of all, let's try to draw the circuit before t equals to 0. So before t equals to 0, the circuit looks something like this. The circuit is something like this. So this is the equivalent circuit before time t equals to 0. So we have a 0.1 farad capacitor here. We have a 2 ohm resistance. Current I is here, plus minus voltage is this, 12 volts and 4 ohms. And this is 0.25 Henry. So now what will happen? So this circuit is in this state for a long time and we don't know, and it means that it means that the inductor will be completely magnetized and this capacitor will be completely charged. Right? So it means that if an inductor is completely magnetized, it acts as a short circuit, and if a capacitor is completely charged, it acts as a open circuit. So the effective equivalent circuit will become something like this. So this is the short circuit. This is something like this. 4 ohms. This is 12 volts. This is 2 ohms. So now this is my V voltage across capacitor at 0 negative, and if I find that this is my inductor current at 0 negative. If I find out the value of this current, it will be the current through the inductor. If I find out this voltage across this 2 ohm resistance, it will be my voltage across the capacitor before time t equals to 0. And this is the current I that flows. So first calculating IL 0 negative is equal to I. So I is equal to 12 volts divided by 4 plus 2, 6, it becomes 2 amperes. So it means that IL 0 negative is 2 amperes. Similarly, we can calculate VC 0 negative is equal to 2 times IL 0 negative, means 2 multiplied by 2, it is 4 volts. So VC 0 negative is 4 volts. So we basically get these two values. So with these two values, we can say that inductor do not change. So after switching, we can say that inductor do not change the value the value of current instantaneously, and capacitor doesn't change its voltage instantaneously. So we can write that IL 0 negative equals to IL 0 positive equals to I 0 positive, and this is equal to 2 amperes. So this is my part A. We can also write that VC 0 negative equals to VC 0 positive equals to V 0 positive, and this is equal to 4 volts, right? So this is the first part of our equation, which we, or the first part of our solution, which we will get. Okay, then how to, so right now let's move ahead and see how we can solve it. So for part B, DI or rate of change of current and rate of change of voltage. So the thing is, we draw the circuit after time t equals to 0. So after time t equals to 0, the circuit is something like this. After time t equals to 0, the circuit is something like this. This is my voltage. This is 0.1 farad. This is 0.25 Henry. This is 4 ohms. This is I. This is 12. Okay, so this is how the current looks like. And remember, I 0 positive is 2 amperes and V 0 positive is 4 volts. So now we have to remember that, or so we have to basically find out DI, rate of change of current, and rate of change of voltage. So remember capacitor equation. So the capacitor current IC equals to C times D VC by dt. And we can also write that IC 0 positive equals to C times dVC 0 positive divided by dt, right? And we know that once this current is flowing in the circuit, the capacitor will not allow instantaneous change in voltage, but it will allow instantaneous change in current. So whatever the current is flowing in the circuit, or whatever the current is in the or the current flowing in the capacitor will be determined by the current across this inductor. So IC0 negative is whatever we have is basically 2 ampere is equal to I0 positive divided by C can give us VC0 positive divided by dt, or it can also be written as V positive by dt. So the rate of change of voltage will be determined by the capacitor. So what we get from here is I0 positive is 2 divided by the capacitance value 0.1, and this thing is equal to 20 volts per second. So this is the value or the rate of change of voltage we get. So this is part B. Similarly, across the inductor, we know that VL 0 positive is equal to L times DI 0 positive by dt, right? And we know that the voltage across the inductor. So we have to find out what is the voltage across this inductor. So let's say this is node A and this is node B. So what is the voltage across these? Or and we can say that voltage across inductor is say VL at 0 positive. So for this, for A B, for, or we can say that between node A and B, or we have to find out the voltage AB. So VAB is given as VA minus VB. So VA is basically 12 volts minus VB is what is determined by VC 0 positive. So VC 0 positive is 4 volts. VC 0 positive 12 volt is this, minus 4 is equal to 8 volts, right? So VAB is 8 volts. So we know that this voltage. So now VAB basically is equal to voltage drop across 4 ohms plus voltage drop across the inductor. So VAB is 8. Voltage drop across 4 volts, 4 ohm resistors is 4 times the current flowing. The current flowing is I0 positive plus VL 0 positive. So what we get here, I0 positive is 2. So we get 8 minus 4 into 2, 8 equals to VL 0 positive, and this becomes equal to 0. So my VL 0 positive is 0. So that makes my DI 0 positive by dt equals to V 0 positive by L, and this becomes equal to 0 amperes per second. So my rate of change of current in this circuit will be determined by the inductor, and that value is 0. So my both answers, again, rate of change of current is 0, rate of change of voltage is 20 volts per second, right? So now moving to part C. So part C, it says that I at infinity and V at infinity. So once the switch is thrown, or the switch is thrown at t equals to infinity, how the circuit will behave at infinity. The circuit after switch throwing will be something like this, right? Circuit will be something like this. Uh, Again, this is the current I, this is the voltage V, this is 0.1 farad, this is 0.25 Henry, this is 4 ohms, this is 12 volts. Okay, so now what we have to find out is the current at infinity and voltage at infinity. Okay, so after time t equals to infinity, the circuit will be, or my inductor will be, again completely magnetized. Completely magnetized. My capacitor will be completely charged. right? So my capacitor is completely charged. It means that it is open circuit. It is completely magnetized. It means that it's a short circuit. So my effective or equivalent circuit would look something like this. Okay, so this will be my VF infinity. This current value will be I of infinity, and this value will be 4 ohms. This value will be 12 ohms, right? So I at infinity, the circuit at infinity will look something like this. So I at infinity will be, there will in this circuit, current I, there will be no current flowing. So no current will be flowing in the circuit. This is the value for my I infinity, and V at infinity, V of infinity will be equivalent to the open circuit or the voltage or the 12 volts. All the voltage will appear across this, or capacitor will be charged to 12 volts. Again, we can see that this at this node and at this node, if this node is charged to 12 volts, this is also 12 volts. There is no current flowing. So my infinite, or at time t equals to 0, my I of infinity will be 0, and my V of infinity, or the voltage at infinity, will be 12 volts. So in this way, we have been able to find out the initial values, the final values, and the rate of change of those initial values with across in this circuit. Okay, so let's solve another example. So this is again an example from the textbook. It is 8.2. In this circuit of figure 8.5, this is 8.5 figure. Calculate IL, or the inductor current at time t equals to 0 positive, capacitor current at 0 positive, and the capacitor voltage at 0 positive, and we are at, or the resistor voltage. So we are basically interested in this resistor, in this inductor, and in this capacitor. Okay, so let's solve this thing. Again, we see that there are two sources. One is a current source and one is a voltage source. So remember, this current source, the waveform is 3 times 3 u of t. So 3 u of t is basically, a u of t is unit step function, unit step function, and this waveform will look something like this. If I have to draw this waveform, so it will look something like this. So this is 3 amperes, this is the current I, and this is with time, this is time t equals to 0. So before time t equals to 0, there is no current in the source, and after time t equals to 0, the unit step function. So this is uh, the current, or this is 3 ampere current flows till infinity. Okay, so let's draw before circuit before time t equals to 0. So before time t equals to 0, it means that there is no this current source. So my effective circuit looks something like this. Okay, we have a capacitor here, we have a voltage source, this, and we have a inductor over here. This is 0.6 Henry. This is plus minus VC. This is 0.5 farad. This is 20 volts. This is plus minus VR, 2 ohms. This is 4 ohms. So, okay. So this is how my circuit looks like. Again, this circuit is in this state since quite a long time. So it means that capacitor, capacitor will be completely charged, or it means that it will be open circuit. Inductor will be short circuit, or completely magnetized. It will be short circuited. Okay, so the effective circuit would look something like this. This will be VC, and this will be IL 0 positive, oh sorry, 0 negative. Okay. IL 0 negative. This is 4 ohm. This is plus minus VR. Okay, so this is how the circuit will look like. I just not have 0. So let's find out the value of what is the value of VR. So VR before switching, we are 0 negative. So we do not have any voltage source connected, or this open circuit is there. It's a short. So VR 0 positive is 0. VR 0 negative is 0. Again, you can easily see that there is nothing that is driving any sort of current across the circuit. Similarly, IL 0 negative, again its value is 0 amperes since it's short circuited, and since there is no current that is source, whether voltage or current source, that is driving any current, so there is no point in it. So the inductor in this case will not be magnetized. It will be having 0 current in this. And capacitor voltage VC0 negative, and this voltage on open circuit voltage, if I'm going to measure voltage over here, minus 20 volt will be appearing, and that minus 20 volt will be cancelling this plus 20, that therefore this whole circuit will be behaving as an open circuit. So this minus 20 volt will appear across this capacitor. Okay, so this is these are my initial values. From these initial values, we have to calculate these 4 values. So we know that inductor current doesn't change instantaneously, so it remains 0 amperes. We know that VC also doesn't change instantaneously, so it remains minus 20 volts. But what about the resistor? So what about the resistor? Okay, so VR 0 positive is not equal to VR 0 negative, because it will change instantaneously if there is any change in the circuit. So let's calculate VR. So VR is 0 positive. Let's calculate that. So after t equals to 0. So after t equals to 0, the circuit looks something like this. It looks something like this. It looks something like this. Okay, so this is 2 ohms. This is 4 ohms. This is 0.5 farad. This is 0.6 henries. Current is I is going here. This is IL. This is 20 volts. This is plus minus VR. This is 3 ampere current source, and I'm not writing U of t because it is we know that it is after t. So the effective after time t equals to 0, the effective circuit would look again. This voltage won't change instantaneously, and this current won't change instantaneously. It means that my effective circuit is something like this at time at t equals to 0 positive. This is something like this. This is 2 ohms. This is 4 ohms. This is open circuit. And this is short circuit at 0. There is no current flowing. This is VC0 positive. Again, minus 20 volts. This is 4 ohm. So what is the effective voltage VR in this case? So my effective voltage will be the calculated by whatever the current I multiply by 2 ohms. So I can easily find out I by current division rule, or CDR. So current divider rule. Just simply apply current divider rule. What we get? Okay, so let's so we have basically 3 amperes coming here, and this 3 ampere will be dividing in 2 ampere branch, 2 ohms branch and 4 ohms branch. Okay, so we have 4 divided by 6 multiplied by 3. So we have uh, 2 amperes flowing here and 1 ampere would be flowing there. So we get VR 0 positive is equivalent to 2 ohms multiplied by 2 ampere. So it is 4 volts. So VR 0 positive will be equivalent to 4 volts, right? Okay. So my first part is complete. So my IL 0 positive is 0 amperes. VC 0 positive is minus 20 volts. And IR this is 4 volts. Okay. So now let's calculate these three terms. Now let's calculate these three terms. So IL, DIL 0 positive by dt. So DIL is 0 positive by dt, or the rate of change of current across inductor. This. So here in this circuit, we know that, or with the current division equation, we know that VL equals to L times DI by dt. So this is the base equation which we get, right? So with this base equation, we can find out that VL 0 positive is equal to, divided by inductance, is equal to IL 0 positive divided by dt. Okay, and what will be the value of VL 0 positive? So VL 0 positive, if we see here, or instantaneously uh, in the circuit, so VL 0 positive is, or for example, what is the voltage across these two, A, B, right? So, and if the voltage will be determined by this capacitor, because capacitor will not be allowing change in, instantaneously change in voltage. Although we see that the resistor voltage is changing instantaneously, but since the capacitor is having more precedence because both are connected sort of semi-parallel, because there is a 4 ohm connected here. So although there is some voltage change across a little branch of resistance over here, but it won't affect the inductor because of the uh, presence of a capacitor in parallel with it. That basically makes that there is no change in voltage across these two nodes, these A dash. So no change in voltage, and therefore VL 0 positive will be equal to, and if we are going to find out, say, this value, and this value will be equivalent to VC 0 positive plus 20 volts, and VC 0 positive is 20 volts plus or minus 20 volts plus 20. So this is equal to 0 again, as what I have said. So this first value, DIL 0 positive divided by dt, is equal to 0 amperes per second. This is my first case. DIL by dt will be 0. Okay. Now basically we have to find out uh, instant or the rate of change of voltage across the capacitor. So for rate of change of voltage across the capacitor, let's move to next part. So again, my equivalent circuit is, uh, let me draw it here. So is something like this. Okay, so this is plus minus VC, this is IL, this is 4 ohms, this is 2 ohms, this is 3 amperes, this is plus minus VR. So let me call it node A and let me call it node B. This is 20 volts. Okay. And we also know that, uh, remember the capacitor equation, IC equals to C times dV by dt. And we can also write it as IC0 positive is equivalent to C times dVC0 positive divided by dt, right? So we can also write it like this. And so now we have to basically find out this value. And IC0 positive, or the current through the capacitor at time t equals to 0 positive, would be determine this value. And remember, the current value through the capacitor will be this. So this is the value of IC, right? And IC0 positive. And remember, voltage across the capacitor would not change instantaneously, but current does. So current does change instantaneously, right? So if we are applying the or sum of currents at node B, so my node B at node B, it looks something like this. It looks something like this. So this is my VC. So there is some current IC going here. This is 4 ohm, and there is some current I coming here, and there is some current IL going in this direction. So this current I call it I at 0 positive, and since this is entering at B, so we can say that I0 positive, it is entering, is equal to IC 0 positive plus IL 0 positive. So remember, the IL 0 positive is equal to 0. So we can say that I0 positive is equal to IC 0 positive. And also, what is the value of this I, the current I that is going here, or the current I that is going here? And this value is what we calculated. We initially calculated that there are 3 amperes here, 2 ampere was flowing here, and 1 ampere was going through here. Remember this current division rule which we calculated. So here we calculated that 2 amperes were flowing through this resistance, and 1 ampere current was flowing through that resistance 4. So this basically at again, I'll solve it for you. So we have this 3 ampere coming here, and we have these two branches of 2 ohms. We have another branch of 4 ohms, and this 4 ohm is connected further with a capacitor and a voltage source, and then there is another something like this, right? And then there is another inductor part that is connected. And remember, this is at I0 positive, this is short circuit, IL 0 positive, and this is open circuit voltage, no current. So this basically, if 2 amperes is flowing here, 1 ampere will be flowing here. So IC 0 positive will be equal to 1 ampere. So this is the value of IC 0 positive. So I can just simply put in the value IC is 0 positive divided by C will be equal to dVC 0 positive divided by dt. This is 1 ampere divided by the voltage uh, or the capacitor. This is 0.5 farad. This is dVC 0 positive by dt. So this value comes out to be 2 volts per second. This is my dVC by dt at 0 positive. This is how I calculate. So I have calculated this. I have calculated this. So now let's calculate D or the rate of change of voltage across the resistor, or what is the or how this value of rate of change of voltage basically changes across this resistor. So um, developing the circuit again. Uh, my circuit looks something again like this. So this is my resistance or of choice where I have to do all the analysis. This is 4 ohms. Again, this is the capacitor, and here is my inductor. So this is so IL 0 positive is flowing here. VC 0 positive is appearing here. This is 20 volts, and I have to we have to basically calculate this voltage. So now, if so, this is basically 3 ohms. So let's consider this loop, right? And write down the KVL, and if we apply KVL at this loop. So I call it as loop 1, apply at loop 1. So applying KVL at loop 1 will get minus VR plus you can say VAB. Yes, VAB plus VC plus 20 equals to 0, right? Okay, this is how this thing will look like. So if I differentiate this, and again, this becomes VR 0 positive. This, then we get rate VAB 0 positive divided by dt plus dvc 0 positive by dt, and this equals to 0, right? And we have actually found out v naught. Um, Sorry, so we have basically found out dvc by dt 0 positive, and in our previous slide we found out that this is equivalent to 2 volts. So this is equivalent to 2 volts per second. So simplifying this, we get minus dvr 0 positive by dt, or this thing becomes equal to dvc 0 positive by dt plus times vab 0 positive divided by dt, and this is equal to 2 plus d times vab by dt 0 positive, and this is dvr 0 positive by dt. So this is the equation, or one equation we get. Now basically we have to find out, or we have to develop an equation for you can say for VAB, or find out for or develop equation for d times VAB by dt 0 positive. Now we have to find out or develop an equation for it. So we can use the at node A. So at node A, if we can just simply do the current uh, analysis. So we have 3 amperes entering, and the leaving is VR 0 positive divided by 2 plus VAB divided by 4. So this is the equation we have. Now differentiate it. So if we differentiate it, d by dt. So if we differentiate it, we get 0. We get 1 by 2 dvr by dt, and we get 1 by 4 dv AB by dt again at 0 positive. So from this relationship, we can see that d times VAB 0 positive is equivalent to 2 times or minus 2 times dVR dt dt, right? So this is what we can see from these two equations. So now with the help of these two equations, we can just simply say that dVR 0 positive equals to 2 minus 2 times dVR 0 positive by dt, and from this we can easily say that dVR 0 positive by dt is equal to 2 by 3 volts per second. So our third case, the rate of change of voltage with respect to time comes out to be 2 by 3 volts per second. Okay, so this is what we get as a result. So this is what we get as our third value. So di by dt, or di 0 positive by dt, we got 0. Again, di by dt, we got 0. dvc by dt 0 positive, we got 2 volts per second, and dvr by dt, we got 2 by 3 volts per second. So now our last case, calculate IL for infinity, VC for infinity, and VR for infinity. So after time t equals to infinity, or at time t equals to infinity, or however you like to call it. So remember, the capacitor will be open circuited and the inductor will be short circuited, because infinite time would have been passed. So simple case, the easy way is to just simply draw the circuit, and wherever you get a capacitor, keep it open circuit, and wherever you find an inductor, make a short circuit for it. So this is my IL at infinity. This is VC at infinity. This is 4 ohms. This is 2 ohms. This is plus minus VR at infinity. This is 3 amperes. So my effect again, what is the value of VC at infinity? This will be again minus 20 volts. It's open circuited. Whatever the voltage across this terminal will appear, or this capacitor will be charged by at this voltage, right? So this, what will be the voltage across this 2 ohm? So the current I, if we can find I infinity across this, so this I infinity, again current division rule, there is a 4 ohm path and there is a 2 ohm path. So 2 ampere will be flowing here, 1 ampere current will be flowing here. Okay, so this 2 ampere will multiply with this, so we are at infinity, 2 multiplied by 2, it will be 4 volts. So we are at infinity will be equivalent to 4 volts, and IL at infinity, so the inductor current at infinity will be equal, whatever the current that is flowing through this branch, and this branch is equal to 1 ampere. So these are the three values for part C: IL infinity, VC infinity, VR infinity. IL infinity, VC infinity, and VR infinity. This is how you solve this question. So here I finish this like part of the lecture, and in our next lecture we'll start from here onwards. Thank you for listening.